So throughout this course, we've referred to browning reactions. When we talked about cooking a steak, we referred to the browning that happened on the surface of a steak. And this week, we're going to talk about the browning that happens in baking. So in terms of baking, there are really two kinds of browning reactions that we're interested in understanding. One is caramelization, and the other one is Maillard reactions. So let's start with caramelization. So caramelization is just what happens when you heat sugar, white table sugar. And if you remember back to Carmen's crema catalana, you saw how she sprinkled sugar on top and then she heated it to a very high temperature. And the sugar immediately turned brown and it created these very nutty, caramelly, buttery flavors. Now, here is a demo by Daniel Rosenberg where he does the same thing, except he applies way more heat, way more quickly. So he just has a white test tube with white table sugar in it, and as he heats it, it turns first brown and then it immediately turns black, and it passes from these nice nutty flavors that we know from the crema catalana all the way to sort of bitter, nutty, vinegary, sticky flavors. So sugar is just a sucrose molecule, and sucrose is made of fructose and glucose. And so the first thing that happens when we apply heat is that these two molecules fall apart into glucose and fructose. And so here is sort of what these ring structures would look at. And then these ring structures just sort of explode into a wide array of other small molecules. So you can see here the different molecules, and you can see here as a remainder of the 5-ring structure and of the 6-ring structure. And you can see then how they've sort of fallen apart further into smaller molecules. And all of these molecules have different flavors and different smells. And typically in caramelization, the flavors that we're talking about are these sort of sherry, buttery, nutty flavors. And this happens at temperatures of about 165 degrees Celsius or higher. So if we were to take these flavors and kind of put them on what we call a flavor wheel, which is what wine tasters or tasters in general would use when they would try to sort of guide their pinpointing what a flavor is. And here's a flavor wheel with all of the different flavors, everything from earthy to nutty to fruity to flowery. And so caramelization kind of creates these particular flavors that are sort of caramelly and nutty buttery. And so now keep this in mind, because now we're going to move on to Maillard reactions and see what kinds of flavors those create. Maillard reactions, in contrast to caramelization reactions, involve the reaction between sugars and amino acids, and these typically take place at temperatures above 120 degrees Celsius. And so what happens here is that if you, for example, just take milk and heat it, there's going to be sugars in the milk and there's going to be proteins in the milk, amino acids, and the sugars are going to react with the amino acids and create these sort of browner compounds that have nutty flavors. And so you've probably had this, if you've ever had dulce de leche, you've had this exact same thing. And there are a lot of desserts and a lot of sauces that sort of build on this concept of just heating milk and creating these flavors. And so there are many different kinds of amino acids. There's about 20 amino acids, and each of them, the first step would be that the glucose reacts with the amino group on any of the amino acids. And so the amino group is a nucleophile, if you think back to chemistry, and the nucleophile is going to attack the carbon on the glucose here. And this is then going to form a bond, and this is kind of the first step in the Maillard reactions. And after this, there is a whole, again, just an array of different reactions that can happen. The molecule falls apart, it reacts again, it reacts with each other, with other glucoses, with other amino acids, but this is the first step. And so you can imagine then that if there is 20 amino acids, and this is the first step, you can just imagine that there is just a lot of different molecules that can be created, even with this just being the first step. The characteristic feature of Maillard products is that they often contain sulfur and nitrogen, which comes from the amino acids in the protein. And sulfur and protein often contributes these kind of meaty, earthy flavors that we associate with when we cook a steak, and there's sort of this earthy, meaty flavor. And this also then contributes to a lot of the other sort of non-distinct flavors that are very different from the flavors that we get in caramelization. So here again is the flavor wheel, and we've circled all of the possible flavors that you can get from Maillard reactions. And as you can see, this pretty much covers the entire wheel. Everything from the earthy flavors which talked about, but also minty, lemony, flowery flavors. And all of this is possible just from the reaction between glucose and amino acids, which is pretty amazing. Another feature that make Maillard reactions especially interesting from a chemical perspective is that they're often exothermic reactions. So there are two kinds of reactions. There's endothermic and exothermic. And endothermic are when we need to sort of put in heat for the reaction to take place. So when we bake molten chocolate cake, it's basically an endothermic reaction to make it happen. Exothermic reactions produce heat as they happen. And so as Maillard reactions start to happen, they produce heat, and this then leads to more reactions happening. And so this speeds up. And you may have experienced this actually if you've ever made toast. So sometimes you may have experienced that you make toast and you wait and it's not done and it's not done, and then suddenly it's done, and then it's done, and then it's overdone. And it just happened very, very quickly. And this is exactly what happened, is that the Maillard reaction started to take place and they created heat, and then there were so many Maillard reactions, and this turned to the toast going from a nice light brown to just suddenly black. And by the way, as you make toast, there's also the fact as the temperature increases and as the toast gets blacker and blacker, there's also an increase in heat uptake, which speeds up the reactions. Maillard reactions, of course, are not only in baking, they're basically everywhere around us. So here's just some examples. Everything from coffee to popcorn to champagne to a nice cured ham are all places where Maillard reactions have taken place. And in some of these cases, there hasn't even been an addition of heat. So in champagne, for example, the reaction is allowed to take place over so long that the reactions take place anyway, even though there is no input of heat. But all of these sort of earthy flavors that you get in a champagne or in mead, they're all also due to Maillard reactions. So I think from this we can all conclude that Maillard reactions are really yummy, and we preferably just want more of them. So is there a way that we can just make more Maillard reactions? So let's look at the chemistry of this to try to figure this out. So we learned that all of this is due to this amino group attacking the carbon on a glucose. And so if there is a way that we could just speed up this reaction and make it happen more and more often, then presumably we would also be able to make more of the later steps in the Maillard reaction. And so if we look at this, you can think that, let's say you did something to the amino group and you actually made it a better sort of attacker of the carbon. You made it a better nucleophile, to use chemistry language. And you could do this by adding a base. And we have talked about a base before in this lecture. And the base, of course, that should come to mind is baking soda. So baking soda is sodium bicarbonate, and the bicarbonate, when you add it, it would take up, it has a negative charge, so it would react with the hydrogens, and you could imagine how it would react with the hydrogens on the amino group, and this would then make the amino group negative and make it a better attacker at the carbon on the glucose. So you could do this with any base, and in fact when you make pretzels you can brush them with sodium hydroxide, and this is what you do to give them that very dark brown color on the surface, even though the dough, when you break them open, is actually really light. So you can try this, and I encourage all of you to go into your kitchen and try this. You can actually brown onions, and you can try to do this with baking soda and without baking soda. And you can see if the browning actually does speed up with the addition of baking soda. This not only applies to browning onions or to pretzels, it also applies to baking cookies. So if you look at different cookie recipes, you can sometimes see that if you were to sort of calculate how much acid and how much baking soda, i.e. base, there is, and you would sometimes notice that there is an excess of baking soda in recipes. And basically any excess of the baking soda is going to contribute to the browning after it's reacted with the acid to create gas that increases the leavening. And so you can then look at different recipes, and I encourage you to go and do this. So if you look at recipes for white cookies, you will often see that there is baking soda added, but there's also cream of tartar added in about the same amounts. And so the idea is that the cream of tartar reacts with the baking soda, contributing to the leavening, but there's basically no baking soda left over to contribute to the browning. Whereas in a lot of cookies where they turn browner upon baking, And obviously this depends on how long you leave something in the oven. If you leave something in the oven for a long time, it's going to turn brown. But the cookies will get done without browning if you have the right amount of acid to balance out the baking soda. So for example, in the recipe of chocolate chip cookies, there is baking soda, but there's no cream of tartar to neutralize this. And there's still acid in the other ingredients, but not enough to neutralize all of the baking soda. And this is what's contributing to the browner chocolate chip cookies.